Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be discussing relative velocity. This video is a continuation of my series of discussions on motion in 2 dimensions or 3 dimensions, specifically the kinematics or description of motion in 2 or 3 dimensions. Now this one is a little bit of a departure of what I've been doing in this series, in as much as to this point I've largely been focused on describing the motion of an object that is simply tossed or projected, or even maybe has a internal propulsion that gives it a constant acceleration. And essentially the object is thrown from the earth, or thrown off of a building, or shot out of a cannon, all of which are stationary relative to the earth. And then it's being observed by somebody who is in turn stationary, standing still on the earth. Today's video is a little departure in as much as what we want to do is consider what would motion look like from the perspective of somebody on the earth if the object was, say, thrown or tossed or otherwise projected by, say, a moving helicopter or a moving car or a person running. And on the other hand, what might the motion look like for an observer in another helicopter or car or what have you that is also moving? So this kind of ties those ideas together a little bit. In order to begin, we need to consider displacements again. Let's say that I have an observer standing here at the origin, X with an O over it for origin position. Now let's say that I happen to have a vehicle right here. Maybe this is a car. What would the displacement be to this car? Well, it would basically just be whatever this vector is that points from origin to car. We could call this X sub OC, okay? And now maybe over here somewhere else there happens to be a motorcycle. We'll call this the motorcycle. And the displacement from the origin to that motorcycle would be represented by this vector right here. So we could call this XOM. Now this origin point was in some sense arbitrarily chosen. Maybe I have a person, like a police officer, standing by an intersection watching everything, and they're just stationary, sitting there by the side of the road. But I could easily have chosen my origin to be this car, in which case I would have a displacement to the motorcycle represented by this vector right here. So we could call this vector right here X car motorcycle. Now, if we were to do a little bit of algebra, it should be apparent that X from origin or officer to car and X from car to motorcycle add up to be X from origin or officer to the motorcycle. So just looking at the triangle that I've drawn, I can say that XOM is XOC plus XCM. I was just doing basic tip-to-tail addition of vectors. Okay, that also means that if I wanted to figure out what this latter term is from the perspective of the person standing at the origin, I can rearrange the equation to get that X from car to motorcycle is X from origin to motorcycle minus X from origin to car. Okay, so I have in some sense a relative displacement for X from car to motorcycle with reference to my original origin. So far, all that I've done here is just basic vector addition. Nothing that I've done here has any special reference to physics formula or to the laws of kinematics in order to set these equations up. I've just basically done vector resolution but with displacement vectors. And instead of saying that something has moved from one location to another, I've simply said, well, one thing is at one location, one thing is at another location, and I have an observer stationary at a third location. So let's consider now what would happen if everything is allowed to move. Maybe the observer is stationary, but the other two move about. So maybe, we'll do this in green, maybe this car happens to move from here to here, and this motorcycle happens to move from here to here. Okay, so those are like your displacements for the car and for the motorcycle. So this right here might be delta x from origin and car. This should be delta x from origin to motorcycle. If I were to draw an arrow that essentially gives me the final position to the final position, that would be like my final displacement between these two. If I put the two vectors together though, so that I have this vector here and this vector here, delta x from origin to motorcycle and delta x from origin to car, then once again I can define a vector delta x from car to motorcycle. In other words, what is the change in displacement between the car and the motorcycle as both of these things have moved? And just as I did down here, where I noticed that x from origin to car plus x from car to motorcycle gave me x from origin to motorcycle, the same thing is true up here, where I can write that delta x from origin to car plus delta x from car to motorcycle is delta x from origin to motorcycle. And thus, once again, I can find that the change in displacement between the two, the delta x car to motorcycle, must be delta x from origin to motorcycle minus delta x from origin to car. So once again, I've just done vector resolution here. Once again, I have an equation that relates the displacement between two objects that are both far from the origin or both removed from the origin with respect to their displacements from the origin. Now I take this one step further. I know that if I have things moving, if I have a displacement of an object, then that happens in time, and I can get the velocity by dividing everything by time. I can come back in here, I can divide everything by a delta time. But now I just have delta x over delta t a bunch of times. That means that I really have a velocity. Velocity of the motorcycle relative to the car is the velocity of the motorcycle relative to the origin minus the velocity of the car relative to the origin. Okay? And that solves it. That lets me get what we call relative velocities. This right here would be relative velocity of the car relative to, of the motorcycle relative to the car. All right. So, simple example. I'm not even going to write anything for this example. Suppose that you're on the freeway. You're driving on the freeway and you go to pass a semi-truck. The semi-truck is traveling at 65 miles per hour and you're traveling at 75 miles per hour. You're both moving in the same direction. How fast are you going as viewed by the semi-truck driver? In other words, at what rate do you seem to be overtaking the semi-truck? Well, the answer is you're going 75 as observed by, say, a policeman sitting by the side of the road in a speed trap. The semi-truck is going 65 miles per hour, observed by that same policeman. So your velocity relative to the semi-trucks is the difference in those two velocities, 10 miles per hour. If we do it in feet per second, you have a semi-truck with a 55-foot trailer, maybe the whole vehicle length is 70 feet, something like that, and you are traveling at 20 feet per second relative to the semi-truck, then from the time that you reach the back of the trailer to the time when you reach the front of the semi-truck is 70 feet divided by 20 feet per second. That's 3.5 seconds. That's how long it takes for you, not really to pass him, but to move from the back of the semi-truck to the front. Maybe add another second or so for the actual act of passing, right? The back of your car has to have cleared the front of the semi-truck with some space between before you can get back over. So this takes 3.5 seconds plus maybe one more second for actually clearing the semi. Okay, that's relative velocity. Another common example is stuff like airplanes or hang gliders or what have you, and there's wind traveling some direction, or maybe a person rowing a boat in a river. So let's say that I have a river like this, and the river itself is flowing such that V river Earth is maybe like 1.2 meters per second. And I happen to have a boat that is trying to row across the river, and the boat is rowing with V boat river of maybe 2 meters per second. Then if I have somebody sitting by the side of the shore and watching the boat, its actual apparent progress will be in this direction here, V river Earth. We can write that V river Earth is V boat river plus this is V boat Earth. V boat Earth is V boat river plus V river Earth. Now notice that these are in fact velocities, so we would have to do vector resolution using angles and directions. If one of these is due north and the other is due east, then we might write the boat river and river Earth like this, and our V boat Earth would therefore be 1.2, 2.0 meters per second. Or in other words, V boat Earth is 2.3 meters per second, 59 degrees north of east. Thanks for watching.